Please, Michelle.
So thank you so much, both for the invitation and the introduction. Am I too loud, too quiet? No. All right. So first, let me begin by thanking the National Science Foundation in the U.S. for sponsoring the research and the SPCSchool for inviting me. I'm very happy to be here. Let's see if I can find a place to stand without like shining in my eyes. So I'm sorry? In front? Okay. So the topic of my talk today is information theory for large networks. And I thought I would tell you about some simple tools that we can use to study very large networks in addition to small networks that have been studied traditionally. But let me begin with the beginning. So information theory began with Shannon's investigation of probably the smallest network that you can imagine, a network with just 2 communicators. In fact, it's not only a network with just 2 communicators, but communication goes only one direction. So we have a single transmitter and a single receiver and some notion of noise occurring in this system. And of course, Shannon derived the capacity of that channel back in 1948. Since then, we've tried to think about networks with more communicators. Obviously, there aren't very many 2-node networks in the world, and so we'd like to understand what can information theory say about larger networks. And there are many possible models that you can consider, and I'll come back to this picture again and again, but these are just a few examples of the kinds of networks that you might consider. So for example, you might imagine a network in which every message has multiple receivers who are interested in receiving that message, as well as a subset of networks in which every message has only a single receiver interested in reconstructing that message, and so on. There are many possibilities. When we started, we as a field, started looking at network information theory, we started with very, very small examples. In particular, 3-node networks. It was sort of the next obvious step after 2-node networks, maybe. And here are just a few examples. This is a broadcast channel. So here we have a single transmitter and a pair of receivers instead of a single receiver. And we asked how much information can we get to this pair of receivers. And we allow different kinds of information. There might be information that only the first receiver wants, information only the second receiver wants, and there might likewise be information that they both want simultaneously. And again, we ask how much information can we hope to transmit reliably in this system. In the multiple access channel, we switch it around. Instead of 2 receivers, we have 2 transmitters. And we ask if 2 people are trying to communicate with you through some sort of noisy medium, how much information can they reliably transmit simultaneously. So if your 2 friends are speaking at you at the same time, there may be conflict. You may hear some noisy version in which they conflict with each other, and you'd like to understand how much information you can reliably transmit in that system. Likewise, this is a relay channel. Here we have a single transmitter and a single receiver, but some sort of helper node whose transmissions are intended to help in transmitting the message from the transmitter to the receiver. He starts with no messages and desires to reconstruct no messages, but he may also interfere with the transmission that's happening. So he's trying to help, but may also be creating noise, and you'd like to understand how much you can communicate. This is the interference channel. Now we have 2 transmitters, 2 receivers. You can imagine everybody trying to talk with everybody with all different kinds of messages. And again, we ask how much information can you reliably transmit in this system. Along the way, so the study of these networks shown here happened mostly, or started mostly in the 70s and early 80s and has continued to this day. In the meantime, we've also studied many other kinds of network systems, and this is that same picture again. You can think of the networks that we've studied as some sort of walk through this very complicated space, and we've studied some examples, but so far don't have a lot of understanding of the space as a whole. And that's what I'd like to talk about today. What we do have is a lot of beautiful results, and I've listed only a very small number of them here. So early papers on the broadcast channel, the multiple access channel, the interference channel, and so on. We also have examples where people have studied very large networks. So what happens is the number of nodes in your network grows very, very big, and the limit, what can we say about the capacity of this network? Also the network coding model, and so on, which I'll tell you more about as we go through. The main point, though, of all these slides is that there are many challenges left that we'd like to conquer. There's a lot of work left to be done. This field is by no means completed. And here are just a few of the challenges that we face. So maybe the first challenge that struck me is that the networks that we understand best are either very, very small. We still don't understand all the 3-node networks completely. Or they're asymptotically large, so we have some understanding about what happens when the number of nodes in your network grows to infinity. But in fact, most real networks are somewhere in between. Most real networks don't have 3 nodes, and they also likewise don't have an infinite number of nodes. They have some very large number of nodes, and we'd like to be able to understand how to derive information theoretic results for those real networks. And to give you some idea as to how big real networks are, this is a plot. It's actually quite old, as you can see from the axis here, but this is the year, and this is the number of nodes in the network. And you can see, and it's an exponential scale, and you can see that the number of nodes in the internet is growing very, very quickly. And yet, it's still not in the either infinite regime, it's also not in the 3-node regime. So we'd like to be able to say things about that kind of network with our information theoretic tools. So that's the first challenge. Why is it? Yes, please.
At what kind of end do you think that infinite results will kick in?
Yeah, it's a good question. I don't know. But I don't think those results tell you a lot about real networks. I mean, you'd like to, for example, have an information theoretic tool where you say, look, I'm thinking about changing my network. I'm thinking about adding a new node to the wireless network. Where should I put it? And you'd like to say something about, which is a good idea from an information theoretic capacity kind of perspective. Which one will give me the biggest potential? Those kinds of infinite results don't give you insight. So they do give you insight about scaling, the kinds of scaling that you get, but they don't give you a tool that will allow you to study a real network today. And frankly, I find it a little embarrassing, if I may. People who build chips can analyze a chip with millions of individual components. Why can't we do the same in information theory, right? Why is it that I can't put down a picture model of a network with 1 million nodes and some sort of model of the communication medium between them? We'd like to be able to analyze that and be able to compare different network designs to each other, for example. Right now we don't have the tools to do that, but we should. We ought to be working towards that goal, I believe. A third challenge for why we are where we are today is that capacities don't compose. And what I mean by that is you might think that if I study the capacity of one small network and I study the capacity of another small network, that should tell me about the capacity of any network that I can build out of those 2 small networks. And it turns out that's not the case. That is, if you know the capacity of one channel and you know the capacity of another channel and you build a network, even a very, very simple network, out of those 2 components, it turns out that the capacities of the individual components don't predict the capacity of the network as a whole. They give you a lower bound. You certainly can do as well as if you operated each of these channels at its individual capacity. But that lower bound is not tight in general. In fact, sometimes what you should be doing is not operating each channel at its capacity, but operating each channel at much greater than its capacity. Sometimes you can get reliable communication that way. And let me show you in an example. Before I show you that example, though, notice what this means. It means that even if you really get a handle on small components and understand their capacities, that won't be enough. You won't be able to just glue them together and understand the capacities of large networks made out of those individual channels. So I have actually 2 examples to illustrate this point. And the first example is very simple. Imagine that we have 2 point-to-point channels. So this is a channel with a single transmitter and a single receiver. Pick your favorite point-to-point channel, maybe the Gaussian, the binary symmetric, whatever it is. And then imagine that you have a second channel of the same type, but independent of the first. So you have 2 Gaussian channels in parallel, say, over which you want to communicate reliably. And consider 2 possible strategies for communicating over this network that I've created by just putting these 2 channels in parallel to each other. So our goal is to get as much information as possible from node 1 to node 2. We're going to have the same constraints that Shannon had, so we need it to be reliable in the asymptotic sense. So if we go to a large enough block length, we should be able to make the probability of error arbitrarily small. And we want to ask ourselves the question, how much information can I reliably transmit over this pair of channels? And here are 2 different ways that you might build a code to communicate over this network. So in the first way, we'll use sort of the intuitive approach we'll pick some rate R, any rate R less than the capacity. Think of it being very close to the capacity C, so R is approximately the capacity of the individual channel. Remember that these two channels, whatever they are, have the same statistics as each other, they're just independent. So they have the same capacity. So one thing that we can do is design two different code books, one for reliable communication over the top channel, and the other for reliable communication over the bottom channel. So imagine that we're going to use some block length n. We'll have n channel uses for the top channel and n channel uses for the bottom channel, and we'll have 2 to the nr different code words if we're communicating at rate r. R is some value close to c. So we have 2 to the nr different code words. We can send the code word associated with the first message or the first half of our message across the top channel, the code word associated with the second half of our message across the second channel, and communicate in total at a rate of 2r. R over the top channel and R over the bottom channel. That's sort of what you would think of if you know what the capacity of this channel is. You'll design channel codes that approach that capacity. And we know, of course, that that is a reliable mechanism for communication. Here's an alternative approach. Instead of treating these two different channels as separate communication media over which we can communicate n uses each, let's think of them as 2 n uses of a channel with the same statistics. So we're using, say, a Gaussian channel and a Gaussian channel, so we'll just think that we have in total available to us 2 n uses of a Gaussian channel. So what am I going to do now? Instead of designing two separate code books, each at rate r and block length n, I'm going to design a single code book, now at block length 2n, because in n time steps I get 2n total uses of a Gaussian channel. And I will pick one of 2 to the 2nr messages. Again, this is a rate r code book, but now it has a block length 2n. So I have 2 to the 2nr possible messages that I can transmit. I'll choose whichever one goes with my 2 times r times n bits that I'm trying to communicate. Maybe it's this one. And I will send the first half of that code word over the top channel and the second half of that code word over the bottom channel. Or you can do evens and odds. You can distribute it however you want. So we'll transmit a block length 2n code over this pair of channels as opposed to using 2 block length n code books, 1 over each channel. And now you ask yourself the question, how do these strategies compare to each other? In the first case, reliable communication was obvious. We had built these codes to be reliable, and so we could reliably decode what went over the first channel and reliably decode what went over the second channel, giving us a reliable decoding of all the messages in total. In this case, though, reliable decoding is actually not possible on either channel individually. You'll notice that instead of having 2 nr possible messages that are going over the first channel, if I'm now sending the first half of each code word over the first channel, I have 2 to the 2 nr possible messages going over the first channel alone. That is, I'm communicating over that first channel at twice its capacity. And reliable communication at twice the capacity is certainly not possible. However, at the same time, I'm sending 1 of 2 to the 2 nr messages across the second channel as well. And if I combine those two outputs, I have 1 of 2 to the 2 nr messages over 2 n uses of a channel with the same statistics, and therefore reliable communication is possible if I decode those two outputs together. Now you might ask yourself, okay, these are 2 different strategies. Neither one looks particularly better than the other in the sense that each one is getting a total of 2r bits across. This one, or a rate of 2r across. This one was getting nr over the first and nr over the second for 2r rate total. And this one is getting 2nr over the pair. Again, the rate is 2r in total. And so the rate of these two strategies is identical. But I claim that the second strategy is much better than the first. The second strategy is better because I get a block length 2n, and we know that our error exponent decays exponentially in the block length. So getting an error probability associated with block length twice as large is a much, much smaller error probability. We got that much, much smaller error probability by giving up the notion that we have to reliably communicate over each channel individually. There's no need to be able to decode this information alone because no node gets this information alone in this particular network. And likewise for the bottom link. What the example illustrates is that sometimes it's better to operate your channels not only a little bit higher than their capacity, but in fact much, much higher than their capacity. Give up the idea that you have to individually be able to decode, reliably reconstruct the information on any single channel, and just worry about reliably reconstructing the messages, end to end, for whichever messages you happen to be transmitting in your system. Now that's the first example, and in that example you don't gain any rate, you only gain an error probability. It's sort of a second order benefit. But I'll argue in another example that in some cases you gain enormously in rate as well. In some cases, communicating at the capacity of your channel is disastrously bad compared to what the true capacity of your network could have been. And here's one simple example where that comes up. So imagine now, instead of 2 point-to-point channels, I'm again going to put together 2 channels, but in this case my first channel is a broadcast channel, and my second channel is a multiple access channel. And again, to keep the example simple, I'm only going to worry about communicating end-to-end. So my goal is to maximize how much information I can reliably transmit from the node 1 to the node 4 in this system. So we're trying to get through as much information as possible. And I'm going to use as my models of these 2 channels very simple models. I've chosen them to make a point, but here it is. So the first channel, the broadcast channel, has a transmission x1, so this is the value transmitted by node 1, and nodes 2 and nodes 3 receive noisy versions of x1, so x1 plus z is received by node 2, and x1 minus z is received by node 3, where z is a Gaussian random variable. So this is a Gaussian broadcast channel. It's a simple example for which we happen to know the capacity. We don't know it for all broadcast channels, but we do for all Gaussian broadcast channels, so I use this very simple case. And then node 4 is just going to get the noise, not even any noise, just the sum of what's transmitted by node 2 and node 3. So the output at node 4 is just the sum of the transmissions from node 2 and node 3. Now, if you look at this system and you say, aha, I know the capacity of this channel, that capacity should be an upper limit on how much information I can get through end to end. Let's see what is the maximal sum rate, that is total rate, that I can get from this node to this node, that node, or received by both. How much information in total can I get through this channel? And that total information isn't hard to calculate. It's some function of the power at which you transmit and the noise of this Gaussian random variable z. I'll denote the noise by n. So we know that the total rate that you can get through this broadcast channel is 1/2 log 1 plus p over n. That's the maximal information you can get through a Gaussian channel. So you'd think, okay, end to end, at most I should be able to get through this 1/2 log 1 plus p over n. But in fact, that's incorrect. The end-to-end capacity of this particular network is infinite. That is, there's no limit on how much information can be transmitted through end-to-end because I chose a simple example where that's possible. How can you see that that's the case? Notice that this guy gets x1 plus z, and this one gets x1 minus z. And this guy receives just the sum of whatever is transmitted by these guys. So imagine that they just retransmit whatever they've received. Node 2 retransmits x1 plus z, node 3 retransmits x1 minus z, x1 plus z plus x1 minus z gives you 2x1. There's no noise left. This is a continuous random variable which you've transmitted end to end through this communication system without noise. You've gotten an infinite amount of rate through this system. Now obviously this is an artificial example, but it's an artificial example chosen to make a point, and the point is not artificial. That is, there are real networks where communicating at the capacity of the individual components in your network gives you a big loss, in this case actually an infinite loss, compared to the end-to-end performance you could have observed in your network as a whole. This is good news and bad news. It means that understanding the capacities of individual components gives you something you can do in a larger system. But in fact, if we take into account the whole network, or at least a larger picture of that network, we can actually get through much more rate through our networks than the individual capacities of channels would predict. So good news for us, we can communicate a lot of information, but bad news in the sense that, boy, we have a lot to figure out now. Because it's not enough now to understand the capacity of a broadcast channel or to understand the capacity of a multiple access channel, to understand networks made from those components. Somehow we're going to have to do better. We'll have to try and understand the network as a whole. There was a question.
When you say that individual capacities, you're actually putting more decoding constraints, right? Because in this case, so you're actually changing the problem a bit and saying that, oh, if you do that, that's not a good thing. But on the other hand, if you allow, say, users 2 and 3 to cooperatively decode in this case, they still have point where different capacity.
So nodes 2 and 3 have no means of communicating in this system at all.
Yeah, but they could cooperate through 4. I mean, like,
that's right. So if you use the capacity of this channel to try and predict what's going to happen, you're forcing them to decode. I mean, that's the definition of capacity. So if you're using the definition of capacity, you're saying, look, how much information can nodes 2 and 3 reliably decode? So yes, the definition of capacity works for the system as a whole, but no, the definition of individual capacity here doesn't help you. Because the individual capacity only tells you how much nodes 2 and 3 can reliably decode, and in fact, they shouldn't be able to decode if your goal is to transmit end-to-end. At least that's an artificial constraint. It's a constraint that you don't need for the end-to-end system, but it's in the very definition of the capacity of that individual channel. The capacity of the channel asks how much information can this node and this node actually decode. That's just the definition of the broadcast capacity.
When you do the cut set out bound or something, you really don't put that.
You don't use the capacity when you do the cut set out.
Yes, that's because you don't have to decode.
That's right. So there are tools that take into account the fact that you can't use capacity, or they don't use the capacity, and we can't use capacity. This just points out that, I think that the historical intuition has been that if we study these small examples, we'll be able to put together the answers to those small problems in getting the answers to bigger problems. And it's true that we can put together the tools from those small problems, the ideas from those small problems, the intuitions, the strategies, and so on, but not the answers. Finding the capacity itself of small channels won't predict anything but a lower bound on the capacities of channels that you can build from those small channels. It gives a lower bound because, sure, if you want, let these nodes decode. But notice that you're adding that constraint. And the same thing happens, by the way, in the multiple access channel. So the multiple access channel capacity model assumes that there are messages that start here and here. And when we use the system end-to-end, there really aren't any messages there. Nobody there is able to decode messages and therefore figure out how to reliably transmit them. And both of those, just the definition of the capacity itself trips us up when we try and put the solutions to these problems together. Thank you. Other questions? Good. All right. So that's another challenge. Understanding the answers to the small questions, the small components of your networks, won't tell you about the large networks. You can think of this as in much the same way that you think of circuit analysis, right? You'd like to be able to understand a capacitor and a resistor and all the different components of your circuit in a way that allows you to put those pieces together and understand the performance of a circuit made out of those individual components. What this example demonstrates is that if you want to have that kind of understanding of individual components that will compose, that will allow you to put these pieces together, capacity isn't the right measure, at least not alone. It tells you something about the individual components, but it doesn't tell you about all their possible behaviors in the larger system. Okay, here's another challenge. Sequential investigation does not scale, by which I mean, if today we suddenly finish all 3-node networks, and tomorrow we manage to solve the 4-node networks, you can see that we still won't make it up to the networks of the sizes that we actually use in practice in any kind of reasonable time. So going through and studying one kind of network at a time, finding some sort of path through this system is very important. It's beautiful work, it's important work, but it somehow doesn't tell us about the picture as a whole. It won't allow us to see the entire picture of network information theory. For example, if there are properties that hold for all of these networks, it's often very difficult to see those properties in going from one example to the next. So if I prove a property of one particular network in this sequential investigation of many kinds of networks, it's not clear when that property is going to hold for other networks and when it's not. So the generalization of our results is difficult when you study these different networks sequentially. There are tools that look at networks as a whole, and the example was brought up previously of cut-set bounds. And there are the traditional cut-set bounds, and there are more modern versions of the cut-set bounds. And again, there are many beautiful results with cut-set bounds. But none of them to date have been shown to be tight in general. And many of them are quite loose. So in many cases, we can find examples that demonstrate that if you take a cut-set bound, for your network that will give you a bound. It gives you a real upper bound, but it's not necessarily anywhere near the true performance of the system. I realize that not all of you have seen cut-set bounds before, and they're not the topic of this talk, but let me just take a minute here to tell you what a cut-set bound is. A cut-set bound is a very simple and beautiful idea. The idea goes something like this. Imagine that you have a network. I haven't actually drawn the network anymore. I've just drawn the nodes in that network. So here's node 1, and node 2, and node 3, and node 4, and node 5, and so on. Oh, I'm sorry, that wasn't a 5. Here's 5. Communicating all through some sort of complicated network, which I just have left out of the picture. In a cut-set bound, you ask the question, how much rate can I get through this system? By asking, how much rate can I get across any cut that I might draw in this system? So imagine that I cut this network into 2 pieces. I'll call the transmitter side S. So here's S. And the receiver side S complement. This is a network with M nodes, apparently. Think of M as a very large number. And I'll ask the question, how much information can these nodes collectively transmit to these nodes over here? Now, of course, they're not transmitting anything collectively. We're just looking for the total amount of rate that node 1 sends to any subset of these nodes, and the total amount of rate that node 2 and node 3 and node 4 and so on send across this line to whichever their receivers may be. And in the cut-set bounds, we find a bound on how much rate that is by imagining that all of these nodes can work together. So they all get to collectively set and choose what they're going to transmit. And all of these nodes can work together, so they can both collectively choose what they're going to transmit and collectively look at what's received by all of them and trying to decode all of their individual messages. That turns this network into a point-to-point network, and then we can apply what we know about point-to-point networks to find a bound on how much rate in total we can get across this boundary. Now, we did this once for some particular cut S. You can imagine doing this for all possible cuts and get bounds on the sums of all kinds of different rates that will give you a bound on the total rate region you can hope for in transmitting information through this system. It's a very simple tool, a very beautiful tool, but unfortunately it doesn't give you tight results in general. So that's something about cut-set bounds. It's a nice general tool. You can apply it to any network, but unfortunately, the results that you get may be very far away from what you can actually achieve. So they will over-predict what's possible by imagining that everybody can coordinate, even though that's not possible in most network systems. So what I'd like to talk about today and tomorrow, in fact, in the 2 lectures, is trying to understand the space of possible networks as a whole. Can we come up with simple ways of thinking about the larger family of networks, or at least large classes of networks? Simple tools to generate these kinds of results. And I have to say, the reason that we don't study bigger networks isn't because, we're stuck in thinking about the small ones. We like them, they're pretty. The reason that we haven't made it to big networks for the most part is because these problems are very, very difficult. Even the 3-node networks, which I showed you at the beginning, all of the examples that I told you are in some sense incompletely solved. The closest to being solved is the multiple access channel, but even that one is incompletely solved. There are things that we don't know even about the 3-node networks. And so it may seem like too much to hope for. How is it that we can hope to understand very, very large networks with millions of nodes, if we can't even master the 3-node networks? And I'd like to present a few tools that I think are helpful in at least making progress in that direction. The main tool that I'll focus on both today and tomorrow is a tool called reduction. And I'm almost embarrassed introducing the idea of reduction to you because it will seem almost too simple to be something interesting, but bear with me. I promise it's a powerful tool, even though it seems very simple, and the fact that it seems very simple should be a good thing. So here's how the idea of reduction works. Many of you have probably seen it before, but probably not in an information theory class, maybe in a computer science, complexity theory kind of class. And here's how the strategy works. Imagine that we have 2 problems. So I'll call them problem A and problem B. Don't worry about what the problems are. Just imagine that you have 2 particular problems that we're interested in. And imagine that if you had a solution for A, you could design a bit of machinery so that combining the solution for A and that machinery would give you a solution for B. Let me say it one more time. So imagine that for any solution for A, there exists a bit of machinery so that combining the solution for A with the extra machinery somehow added around it, gives you a solution for B. If that's possible, we say that problem B reduces to problem A. That is, it's enough to solve problem A, because anytime you have a solution for A, you can turn it into a solution for B. So the problem B reduces to the problem A if the availability of a solution for A would enable the construction of a solution for B. We enabled that construction by adding some machinery. Now, in complexity theory, they use this way of reasoning to think about the relative complexity of two different problems. In particular, they say, well, if this machinery is itself very simple, say linear complexity or some other measure of a very simple extra bit of machinery, then it must be that problem B can't be much more complex than problem A. Because whatever kind of solution we can find for A, we can add some very little simple shell around, say, this computer program to create a solution for B. This one isn't much more complex than this one. So in complexity theory, they use this tool to study the relative complexity, the relative difficulty of solving different problems. How quickly would a computer program that's trying to solve this problem solve that problem? Notice that in order to complete this line of reasoning, it's not actually necessary to have a solution for A. And that's where the power of the technique comes in. So you'll notice that we didn't say, look, I have a solution for A, and here's how I'm going to turn this particular solution into a solution for B. We instead, in the reductive argument, only said if we had a solution for A. I could turn that into something that I could guarantee would be a solution for B. So in complexity theory, they use this very simple reasoning to make a very powerful statement. They can make statements about the complexity, or at least the relative complexity of two problems, even when the complexity of each of them is unknown. So you may not know how hard A is to solve, but you can still say that problem B is not much harder if you can just design this machinery. Machinery that guarantees that any solution for A could be turned into a solution for B. All right, you with me? Ask if there are questions about that, because everything builds from there. Yeah? We're good. All right. So I'd like to suggest that the same very simple tool can be used also in information theory. And by the way, this is a very old tool. It's by no means new, but it hasn't been used very much in information theory, and I'd like to argue that it's a useful tool for our purposes as well. And here's how you might use it, one way that you might use this kind of reasoning in information theory as well. So now imagine that instead of having two problems, you have two networks, network A and network B. And you're interested in understanding something about the capacities of these two networks. We'd like to make the same kind of argument. In particular, we'd like to say that if we have a sequence of codes for A, then I can add a bit of machinery to that sequence of codes for A to turn them into a sequence of codes for B. If you can argue that you can design such a piece of machinery so that any sequence of codes for A can be turned into a sequence of codes for B with the same performance, meaning the same asymptotic error probability and rate, then you can show that any rate that's achievable on A, any rate that you can reliably communicate on A, can also be reliably communicated on B. In particular, you can show that for any point in the capacity region of A, there must be a sequence of codes that achieves that point. If I can add this machinery to turn that sequence of codes into a sequence of codes for B, and that sequence of codes also has an asymptotically negligible error probability and the same rate, then whatever rate was achievable in network A is also achievable in network B. So you can say that the capacity region for network A is a subset or equal to the capacity region of network B. And again, the tool is incredibly powerful because it doesn't rely on you having any idea how to build the codes that achieve the capacity, or even to know what the capacity of the network is. You can show that the capacity region of one network is a subset or equal to the capacity region of the other network without knowing what either of those capacity regions looks like. Just by showing that if you had a code or a sequence of codes for one, you can turn it into a sequence of codes for the other. And if the first was reliable, the second will be reliable as well. So we'll focus here on this machinery. Notice that there's great power then in learning how to design good machinery. We can stop worrying about how to design good codes, and we should worry about that too, but we don't need it to solve results using the reductive strategy. We can instead just focus on, if you had a code, could I turn the code for this network into a code for that network? Just focus on the machinery. And it turns out that designing the machinery is much easier than designing the code. So it'll save you a lot of effort, a lot of work, if you can apply this strategy.
Sorry,
Please.
I don't understand why you want to design a machinery. You need a complexity. You want to know that whether something is computable or not. So this is very important.
But that's not where we are. We're not worrying about complexity. So yes, if you were worrying about complexity, we are just trying to understand properties of capacities of different networks. And I'll show you by way of example, you'll understand. So bear with me a minute. But here, we're using this machinery just as a tool to make very strong statements about capacities of different networks without having to solve those capacities. So we're not making statements about complexity at all. We're making statements about capacities of networks by comparing different networks to each other. So the first example, which we'll come to very shortly, will ask questions like, look, if I add delays to my network, will that change the capacity? That gives me a network A. Oops, I'm pressing the wrong button here. That gives me a network A that might be, oh, I no longer have, oh, there it is. That gives me a network A that might be the network with delays, and a network B that might be the network without delays, or vice versa. And you can compare these two capacities to each other, even if you can't solve either of them, and give a definitive answer to the question, does delay affect capacity?
So essentially you are trying to define a more general setting for degradedness.
Or a way of relating problems to each other that may not be about degradedness. It's a way of using solutions to one problem to tell you something about a solution to another problem. Even when you don't know either of those solutions, you can learn something from the relationship between them. And if you bear with me, there will be plenty of examples. But other questions? Yes, please.
Probably you only need reductions both ways, because sometimes you might say one is content, the other are going to be much, much bigger. So
that's right.
So
sometimes we'll get inner bounds and outer bounds. Sometimes we'll get exact equivalence relationships between them. Either way, they may be useful. So for example, if I don't know the capacity of one network, but I have tools for finding the capacity of another network, it may be useful to say that the capacity of the first network is a subset of one. And sometimes actually we can say it's a subset of one of this type, it's a superset of another of the same type. If we can solve those two bounds, that'll give us upper and lower bounds on the one in the middle. So it's useful.
That doesn't do something obviously bad. Something you be clever, and so you don't lose too much in this.
You will try and get the best bounds that you can, absolutely. But you will, yes. So you'll work your way towards getting the best bounds you can. You'll try and get bounds in between your bounds. When you're doing upper and lower bounds, you'll try and see how close they are to each other, and so on. So yes. But in general, you can get relationships between things that seem related and relationships between things that at first glance seem totally unrelated. And each time, I think, we learn something. Other questions? Thank you. All right. So here's an outline of not just today, the rest of today, which is not very long. I end at 3:30. Is that right? Yes. 3:30? Okay. Right. So here's an outline of the rest of the whole thing, the 2 days. First, we'll spend some time on examples. It'll be much more clear if we can work our way through how these arguments work and give some real examples to see the kinds of results that we can get, and how the arguments in particular work. Then we'll ask the question, well, okay, what does it buy us? You know, what's the importance of finding relationships between different problems in this way? How does it help? You know, what can we do now if we have this tool? What do we do with it? And then at the very end, maybe we'll talk about some conclusions, not today, but tomorrow at the end. So first, let me begin with definitions. And before I even put up the slide, I think if I put up the slide, your first reaction will be to cringe. There are equations everywhere. It looks terrible and awful. It's just definitions. Bear with me. I promise there won't be a quiz at the end. And if we step through the definitions carefully, we'll just all be on the same page as to how I define capacity and what does it mean. So bear with me. I know it's not pretty, but here it is. Okay, so here's my definition of a network. I have this tendency to want to point with my hands, but both hands are full, so I'll try and stick with the pointer. So here's how it looks. Imagine that you have a network, and this network can be anything. So I'm going to assume memory lists to keep life simple, but that's all I'm assuming. So this could be a collection of lossless links. For those of you who heard the network coding talk, I think there was last week, this could be a network of lossless links. It could be a wireless channel. It could be your favorite channel, whatever it may be, or a whole collection of lots of different channels in parallel, in series, whatever you want. But I'm going to write the model of my channel as some distribution on all the outputs given all the inputs. So if it's really lossless links, each output will only depend on the corresponding input and they'll be identical and so on. But in any case, you can represent it by this model. It's just trying to capture everything in a single picture. I'm going to imagine that my network has M nodes. And think of M not as 3, not as 5, but think of the internet or your wireless provider's network. Think of it as having many, many nodes in your network.
I have a question.
Yes, please.
It goes both ways in that channel.
Everybody transmits and everybody receives.
Okay, so you have like probabilities for one side and for the other side also.
Well, all outputs can depend on all inputs, or maybe they don't. Maybe somebody has an alphabet that they transmit with that has alphabet size 1, which means effectively they don't transmit. If you can only say one thing, you're really effectively saying the same thing all the time. It's like saying
Y can send to X, Y, M.
Everybody can send to everybody in the most general case, but you can also imagine this being any specialized network is a special case. It will just be hidden inside this distribution on all outputs.
Because I mean, the input alphabet is not just from the left, and it's from all
That's
possible.
right. Everybody can transmit, everybody can receive. Thank you. And we'll imagine, in fact, that everybody has a single message they're trying to transmit. There's no loss of generality, it turns out, in having just one message from each node. You can just create more nodes if you want to transmit more. But just to keep things simple, let's imagine that everybody has just one message that they want to transmit. So if I'm going to use a block length encode, we'll use WI to represent the message that originates at node I. And if node I is transmitting at some rate, let's call it rate Ri, that means that in a block length encode, WI can take on 1 of 2 to the NRI possible messages. So everybody has something they want to say. If you really have nothing you want to say, your Ri is equal to 0. We can keep it inside this model. Likewise, the source that node I is transmitting, node I also has certain sources that he's interested in reconstructing, any subset of the messages from other nodes in this network, and we'll call that his demand set, DI. So DI is just some subset of 1 through M. He probably doesn't want his own message, but it doesn't matter either way. His own message is easy to reconstruct, given what he knows. So it's just some subset of all the possible messages that are somehow being communicated through this very complicated system. The reconstruction that node I makes of his demand set will be denoted by W hat of D of I. So this is the reconstruction at node I, which will happen only after n time steps. We're using this asymptotic notion of communication established by Shannon. And what is in this? Well, it's just a reconstruction W hat of J for every J in his demand set. So node I wants lots of possible messages going through here. He's going to have to reconstruct all of them at the end. And our probability of error will be the probability of the union of all the error events. So it's the probability that anybody fails to decode any message from any of the other nodes in the network reliably. So anybody fails, even in 1 bit of his message, the whole thing fails. That's our probability of error model. Now, this gives you sort of the skeleton, what happens on the outside. What happens at each time step is denoted here by xt and yt. So at each time t, node I can transmit something to the network. So xt of I is the transmission from node I at time t.
Sorry, for the B, with the probability to get an error on the end step.
The piece of E is the probability that when you decode, which is at the end of all time after n steps, that you get an error, that anybody gets an error. So we won't even attempt to decode until the transmission is done. We're using here a block length n code, so we won't attempt to decode anything until time n. But in the meantime, we're transmitting at every one of those n time steps. Yeah? So at each time step, every node, this is node I, has a transmission. So the transmission from node I is, at time t, is x sub t super I. So I is the node transmitting, t is the time. And likewise, he receives from the network y sub t of I. So x sub t of I is what I transmit if I'm node I. y sub t of I is what I receive if I'm node I. This is both at time step t. And finally, but very importantly, what can I use in deciding what I'm going to transmit? If I'm node I can use my outgoing message because I know that. And I can use anything that I've received in the previous t-1 time steps. But I cannot use anything I'm going to receive at the same time that I'm transmitting, because I have to somehow decide what I'm going to transmit before I transmit it. It's a causality constraint. And I certainly can't use anything that I'm going to know in the future. So I can only use information that arrived to me in past time steps and what I already knew at the beginning of time, which is my outgoing message. All right, any questions about that? Because this model will sort of pervade everything. So we're clear. All right, it's a very basic model. It's the same as Shannon's model. It's just generalized to m nodes, and it's strictly enforcing causality. Your transmission at each time t can depend only on things that you receive in prior time steps. You can't possibly rely on y sub t, what's received at time t, because y sub t relies on what you transmit. So you can't somehow rely on each other. And the capacity of the network will just be the collection of all rates for which there exists a sequence of codes. The sequence of codes is using just larger and larger block lengths with probability of error going to 0. And then, as usual, we'll take the closure of that set. So you don't have to be able to get a rate exactly. If you can get closer and closer and closer to that rate, we'll count that rate inside our capacity region, whether you can build the code at that rate exactly or not. So this is the definition of capacity. Notice now that a capacity is not a single point. It's a region. It's what rate I can send at the same time that Marcelo is sending a rate R2 and you're sending a rate R3 and R4 and R5 and so on. It's what rates we can simultaneously transmit through this network where everybody is somehow maybe interfering with each other because we're all trying to transmit our information through the same medium. Any questions about that? All right, you made it through the hardest slide. It all gets easier now.
Sorry.
Oh, nope, we didn't make it through the hardest slide.
Sorry.
No, please.
Just one message that you split them over all the block length.
So we have a message whose number of bits is n times Ri. So you can think of it as Ri bits per symbol, Ri bits per channel use. So, but we assume that we have that entire message at the beginning of time, no matter how big n is. So we all start with our messages. It's not sort of like, well, you're talking and I'm talking and we're deciding what to say as we receive messages. That's not Shannon's model. His model is we have some stream of information and we're trying to transmit that stream, and we have the stream available to us all in the beginning. So the amount of information we transmit is growing with n, but we know it all at the beginning of time by assumption in this model. Questions? Thank you. Other questions? Good. All right. So we made it through the definition slide. The definition is the shortest section, but the longest time per slide, probably. So let's do an example. So this is the example that I alluded to previously. Imagine that you'd like to understand the answer to a very basic question about capacities of networks, which is how does delay affect the capacity? So we'll consider some network, an arbitrary network, and then we'll add to this network delays. And you know, I've drawn one delay in this example, but you could add delays at every node, at many nodes, at some nodes. But imagine that you add some finite known collection of delays at some subset or all of your receivers. How does that affect the capacity? That's what we'd like to understand. And just to illustrate the point that I made earlier, this is not a new question. People have studied delay in the literature for many years, and I have here some examples dating back to 1995, and then probably earlier examples, but this is just a sampling. There are examples in the literature where people have studied how does delay affect capacity. So in a Gaussian channel, if I have feedback, how does delay in the feedback affect the capacity? How does delay affect the relay channel's capacity, and so on? The way people have traditionally studied this problem is they find the capacity of the network with delay and they find the capacity of the network without delay and they compare them to each other. And that's hard. That's really, really hard. We'd like to do something easier if we can. We'd like to not only do something easier, but we'd like to answer this question for all networks at once. I mean, if we have to study one network at a time to understand the impact of delay, we'll never get there. We'll never really understand what is the impact of delay on network capacity. Now, before I tell you about new results, let me just quickly summarize the old results. Every single one of these papers either says or suggests that delay affects your capacity. Every single one of them says that if you add delay to your network, it can decrease, or it might decrease, the capacity of your network. In some cases, they're bounds. In some cases, they're capacity results. Every one of them suggests that delay can decrease your capacity. And you can see why people would be worried about this. Imagine that we have just a very simple network. I'll draw just a 2-node network here because it's the simplest picture that I can draw. And imagine that we've designed a code for this network when that network had no delays. And this is just a reminder of our notation. Let me just step you through it a little bit here. This is just the same notation that you've seen before, just stepping you through each time step. So at time step 1, this is what is transmitted by node 1, appears right here in our table. At time step 1, what's transmitted by node 2 appears at this node. And here's what each one receives. Here's what node 1 receives at time 1, and here's what node 2 receives at time 1. So let's see what they're transmitting. At time 1, we have no past channel outputs. This is the beginning of time, so we don't have anything that occurred in the past. So what node 1 transmits can only be a function of what his outgoing message is. So x1 is just some function of his outgoing message, w1. And likewise, at time 1, node 2 knows nothing except his outgoing message, so he'll transmit at time 1 some function of his outgoing message, and each one will get some channel output. Likewise, at time 2, we now have the transmissions from node 1 and node 2 respectively. What node 1 transmits at time 2 is some function of his outgoing message and past outputs from the channel. His only past output is y1 of 1, so he can use that in deciding what to transmit. Likewise, node 2 has his time 1 channel output, so he can use that in deciding what to transmit. And then each one will receive their time 2 outputs. At time 3, you can rely on times 1 and 2 at each of these nodes in deciding what to transmit, and so on, until time n, when you can rely on all past outputs from your channel. And then at the very end, after time step n, we'll try and reconstruct. So here's the reconstruction at node 1 of all the messages that node 1 was interested in. It's a function of everything he knew, his own outgoing message, and everything he's received from the channel in the first n time steps, all the time steps. And likewise at node 2, and resulting from this whole communication will be some rate R1, R2, and some error probability. Now imagine that we have this code for the network with no delays, and we'd like to understand what's going to happen in the network with delays. And you can see if you try and use the same code, it looks bad. It looks bad very early, and here's the reason why. So imagine now that we have another network that just has a single delay at node 1. You can have as many delays as you want, but to keep things simple, let's imagine that we have just one delay, and it's just at this node 1. So what's going to happen? At time 1, we can do the same thing we did at time 1 in the previous picture. Our messages our transmissions by the 2 nodes only depended on the outgoing messages anyway, so we can transmit the same thing that we transmitted in that case at both of these nodes. But now the output at node 1 is going to be delayed. You'll notice that we have this delay in the output. So instead of receiving that at node 1, we'll have to wait and receive that at node 2. But that's a problem, right? Because if we wanted to transmit what we used to transmit at time 2, we now don't have the information that we need to figure out the function that was supposed to be transmitted at time 2. Remember, that depended upon what was received at time 1. And so if we want to make that transmission, and in fact we want to make both of these transmissions simultaneously because they're going into the network together, they may affect each other in the network, so we want them to be transmitted simultaneously, we can't do that until time 3. Okay, so imagine that we do that at time 3, but now the time 3 output is delayed till time 4, so we can't do what should have happened at time 3 can't be done until time 5, and so on all the way down the line. It takes us twice as much time to send the same code across this network. And spending twice as much time isn't bad for the probability of error. If we use the same code, we'll get the same probability of error that we got before, but it's disastrous for the rate. The rate here is cut in half because it took us twice as many channel uses, and this is how many bits per channel use. We only get half as many if we use twice as much time. You can see why people were worried about the impact of delay on capacity. But in fact, using the model that I gave to you in the previous slide, a few slides back, the really ugly one, we can demonstrate, using the reductive strategy, that delay has no impact on capacity. It never has any impact on capacity, provided that you follow the model that I gave. And I'll talk about what that means about the prior results at the end. Yes?
So you assume that you know the exact amount of the delay?
We assume that we know...
That you do know the amount of the delay?
We assume that we know the delays, yes. We assume that we know the delays and that they're all finite. So we have to know those in advance, yes.
They are bounded to finite.
They are, well, since there are a finite number of receivers, bounded and finite will be the same.
But the block length might change.
Oh, in our delay model, it's not a function of the block length. It's just finding the capacity for all, over all block lengths with delay or without delay.
And the delay is respective of the block length.
The delay is independent of the block length, yes. It's a function of the network, not the block length over which you code. Question?
So in the previous slide,
This one.
yeah, but the second one knows Y1, so it can
Yes.
transmit in the second, and you can make a kind of a pipeline. You need one more.
So yes, he could have transmitted here,
Yes, and then it will be missing.
but if he's not transmitting at the same time, we don't know that our code will decode properly.
We could do two.
and the asset would be like a pipeline. So
Yes, and that's something like what we will do. Yes. So I won't talk more about that until we get there, but I promise I will get back to that idea of this pipelining. Other questions? But it does not, in fact, rely. You never want node 2 to transmit alone what his time 2 times transmission would have been, because if these two aren't transmitting at the same time, then we're in trouble. If they're not transmitting at the same time, it's no longer this code, then we have to reevaluate what's going to happen to our error probability. So we'll get there, I promise. Yes, please.
Just about the delay, I mean, if node 2 is transmitting without delay, can't we use the same kind of channel for node 1? I mean, it's just for the assumption of copy.
Yeah, so how is it that node 1 has a delay and node 2 does not? Yeah, sometimes this is a real physical reason. I mean, this may be the location, how long it takes for the information to get from one. Not in general, no. But it turns out that capacity-wise it won't matter, which is in some sense preventing
No,
it.
it's memoryless, then it won't matter.
This network is memoryless, and all of the networks studied in these examples are memoryless, and yet they all suggest that it does matter.
But if it's memoryless, how come it's remembering what Y was?
Oh, it's not an issue. So the nodes don't. The nodes have memory. It's the channel that's memoryless.
Oh.
I'm sorry. Yes. So the nodes all can remember everything. In fact, they are. The transmission at each time depends on everything that he saw in the past. So the nodes have memory. But the channel itself, what it comes out of the channel at time t, only depends on what went into the channel at time t.
And we're not concerned about the memory of the node? I mean, is it?
So that's a separate question. In Shannon's model, he didn't worry about resources, so computation was free. He didn't worry about bounding it. It's disregarding it in this model, but if you wanted to take it into account, the answers would change, presumably.
Even for an n, so in your result, even for an n, the achiever rate is a bit less than for one case than the other, right?
Say it again.
So for a given n, the achiever result for one case is a bit less than the other.
It will be slightly less, but capacity is only defined in the asymptotics.
I think the difference is there actually.
Yeah, you'll see it when we get there. Yes, absolutely. All right. So let's see. So this is why people were worried, right? Because it looks like you're going to get further and further behind if you try and code over networks with delay. But as I said, delay has no impact on capacity with our model. And that, I want to underline that point, that for any network that fits into our model, which is quite broad, delay has no impact on capacity. If you start to violate things like causality, our model says nothing about that case. Okay, so let's prove this result, and we'll do the whole proof here. I promise it won't hurt. And here's how the proof goes. Step 1 is just an inductive argument. So my claim in step 1 is that you really only have to prove this result for a single delay. Proving it for a single delay is no different than proving it for any finite known collection of delays. And how do you argue that? Well, if no single delay has an impact on capacity, then there's no difference between the capacity of the network with no delays and the capacity of the network with one delay. And likewise, by the same result, there's no difference between the capacity of the network with one delay and the capacity of the network with two delays. And likewise for 3 delays and 4 delays, and you keep going until you hit all of the delays in your network. If you can prove that no single delay has an impact on capacity, then the single delay by which these two networks differ will have no impact on capacity, and the single delay between the next two networks will have no impact on capacity, and so on. So if no single delay has an impact on capacity, then no finite known collection of delays has an impact on capacity. We're always assuming that that delays are known to us in advance. All right, so step 2 will be to show that the capacity region of the network with delays is a subset or equal to the capacity region of the network without delays. This is the same as saying delays can't help. Adding delays doesn't increase your capacity region, which, it seems obvious, but let's use a reductive argument to actually prove that that's true. It's trivial, but let's do it anyway. So here's how it works. So in the reductive argument, we want to imagine that we have a code for the network with delays. And here is my code for the network with delays. You don't really have to know how to design a code. You just have to imagine that you have one. So imagine that I have some code for the network with delays, and you'll notice that it's working in the way that a code for a network with delays has to work, which is to say that at time 2, node 1 can't transmit an output that's dependent on what it should have received at time 1, because it didn't get anything at time 1. It won't receive that information until time 2, so in order to remain causal, it can only rely on what it already knows, which is the message itself. Node 2, on the other hand, can rely on everything it knows from the past, so it will use all the information available to it in deciding what to transmit at time 2. Likewise, at time step 3, we can use only what we know at each of these nodes. So node 1 at time 3 knows the information associated with time step 1, but doesn't know the information associated with time step 2, so it'll only use its channel output at time 1. This one will use information from both time steps 1 and 2 because it's already received both of those, and so on. Okay, so we have this code, whatever this code is. It has some particular rate, and it has some particular error probability. For the reductive argument, we just want to show that we can use this code to design a code for the other network. Now it's the network without delays, that will have asymptotically the same rate and error probability. In this case, we'll have exactly the same rate and error probability. So how do we do that? Well, it's trivial. We just use the code exactly as it was. So you'll notice here, at time 1, we transmit our time 1 transmissions as usual. Nothing has changed. At time 2, we had this information, but the code that we're applying came from the previous network, and that code didn't have this information. We just want to use the same code. So we'll just go ahead and use the code that doesn't rely on information we have. We're perfectly capable of ignoring this information. It's available to us, but we won't use it. We'll just go ahead and use the code exactly as it was in the previous slide, which will give us exactly the same rate and exactly the same error probability. What does this tell us? It tells us that for any rate vector in the capacity region for the network with delays, there's some sequence of codes, and those codes can be run on the network without delays with exactly the same rate and error probability. Therefore, any rate point in this region is also in this region. In other words, the capacity region for the network with delays is a subset or equal to the capacity region of the network without delays. Not surprising at all. Delay doesn't help. We know it's a subset or equal to. What we really care about is does it hurt, but this is half the argument that we need to make. The other half the argument is the reverse. We'd like to say that if you have a code for a network that has no delays, we can run that on the network with delays and still get asymptotically the same error probability and the same rate. And you remember that we started this process before. We had a code for a network without delays, and we tried running it, and we noticed that we sort of ended up transmitting only on the odd time steps. That is, transmitting at time 1 was no problem, but then we had to wait for the message until it arrived at time 2, which meant we couldn't use it until time 3 because of our causality constraint. And then we used the time 2 transmission, and then we had to wait around, and we couldn't use that until time 5 and time 7, and so on. We could only transmit on the odd time steps using the code that was designed for a network without delays. But here's what we're going to do, and I think that this is the strategy that was suggested earlier. Why leave the even time steps blank? I mean, why not transmit something else during those time steps? So here's what we're going to do. Instead of using the block length n code from the network with delays to design a block length n code for the network without delays, let's use the block length n code from the network with delays to design a code for the network without delays that has a larger block length. It turns out the block length will be a little bit larger than twice as large, and I'll tell you about that little bit larger in just a minute. It's roughly 2n. How are we going to do that? Well, we'll take our message, and we'll think of it as being a block length 2n message, but we'll break it up into its first NR1 bits and its second NR1 bits. So we'll just break our messages in half. And we'll use the block length n code in the odd time steps to just transmit the first half of each message, and then transmit whatever results from the first half of each message, and so on. And likewise, in the even time steps, we'll use exactly the same code, but on a totally different message, now the second half of our bits. So we'll use the same code on the second half of each message. And you'll notice that what interleaving these two codes does is it gives us the waiting time that we need in order to be ready to transmit the next time step of our particular code. So we transmit, we sit around and wait while the other message gets transmitted, and then we're ready to do our next transmission. Then we sit around and wait while the other guy does his transmission, or the other half of our message does his transmission, and so on. We'll do that all the way down the road. It'll take us 2n time steps to do all of our transmission, and then we'll need one more time step to sit around and wait for that last Y to be received. We need all the Ys because the decoder for the network without delays had all the Ys. We need all the Ys also. So we'll use a total of 2n plus 1 time steps. And what will that do to our rate? Well, our rate will be the old rate times 2n, that's how many bits in total we transmitted, divided by 2n plus 1, that's how many time steps it took us. Asymptotically, this is approaching R1. Likewise, R2 times 2n over 2n plus 1 is asymptotically approaching R2. And the error probability by the union bound is less than or equal to the error probability for the odd half of the messages, and the error probability plus the even half of the messages. Those two sum to at most twice the error probability for each individually. If you had a sequence of codes with probability of error going to 0 before, it's still going to 0 now. So this is a reliable code. It's a reliable code. It runs on the network with a single delay, which tells us that any rate that was achievable on the original network is also achievable on the network with a single delay. And by the inductive argument, we know that a single delay is good enough to show any finite collection of delays. So really what we've just shown is that the capacity of these two networks are the same. This is the network with no delays. This is the network with any finite known collection of delays. And the capacity regions of those two networks are the same. They're the same whether it's a relay channel, a broadcast channel, any kind of channel, network, coding network, and so on. Now you might be asking yourself, okay, how is it possible that this result is true when there are all these other pieces of evidence that suggest that delay does decrease the capacity? And the answer is some of these things are bounds, in which case the bounds are loose, as proven by this result. In other cases, they violated the causality constraint. And if you violate causality, it's pretty clear that delay is going to have a huge impact on capacity. I mean, if I can know what is going to come out of the channel as a function of what I myself am transmitting at that instant in time, it's very easy to construct examples where that knowledge is huge. It makes your capacity very large, and without that knowledge, your capacity is much smaller. So in the case where there's no causality constraint, the capacity can change as a function of delays. But under our model, which allows any any memoryless model for a network with any number of nodes, and any model of the relationship between the inputs and outputs, any memoryless model of the relationships between the inputs and outputs, you can see that delay has no impact on capacity. Now you'll notice that we've proven this result, and yet we have never derived a capacity. We haven't derived a single capacity region for any network. Deriving capacity regions for networks is much harder. So all of these other papers are actually much more difficult than the result, which I've just proven to you in whole. I think this proof was a page or two in a conference paper somewhere. Very easy by using the reductive strategy. Question?
Can you please go back to the previous slide?
One more.
So here the rate is divided, it's R times 2n divided by 2n plus 1, right?
That's right.
This is for a single delay.
This is for a single delay.
So if you add delays, this rate here, this fraction will be added. It will be like 2n divided by 2n plus 2, 2n plus 3.
But our number of delays is not growing with n. It's always finite. So each one will have an asymptotically negligible effect. Yeah? So we're not allowing, our delay has nothing to do with our block length, right? You know, somehow it has a long distance to travel. That doesn't matter whether I'm using a block length 1,000,000 code or a block length 2 code. It's the same distance. So our delay has nothing to do with our block length. So for any finite number, asymptotically there'll be no difference. Yeah? It does rely on the notion of asymptotics. And if you're really worried about delay, you know, if you're trying to decode subject to delay, that's a totally different question, right? You know, if you have a delay constraint under which you're decoding, now you can't take block length to n and so on, a very different question. But the capacity question itself, in this asymptotic sense, how much information we can deliver doesn't take that notion of delay into account, and then the capacities are the same.
So as your n goes to infinity, so...
I'm sorry, I can't hear. Can you speak a little louder?
As your n goes to infinity, so the storage capacity of each node is also unlimited, because you have to storage all everything.
As our block length goes to infinity, yes, each node's storage and computational capabilities are growing very, very large. That's built into Shannon's model. So you can argue, okay, is this a practical model? Is this the right model? And that's a very reasonable and good question. It is an upper limit on what you can do. And that's something useful to know. It tells you sort of, if you had unlimited resources, what could you hope for? And then you can ask different questions. It's no longer a capacity question, but different questions about, okay, now what happens when I'm resource constrained? And those are very, very interesting questions about which we actually know very little. But they're good and important questions to ask.
What about if the delay is a bit random?
If the delay is random, this strategy does not apply. This strategy, this proof strategy, doesn't, you know, we very much relied on knowing when our message would come. I'm not even sure, actually. You know, I thought a little bit about this. The short answer is I don't know. But the longer answer is I thought a little bit about this, and I'm not even sure how to model it in the sense that, you know, what is it that I'm receiving if my delay is random? You know, if it's random and once we can learn it and be done, and that's fine. But if it's
random and unbounded, so random and bounded is support is bounded, then you can always bound by the maximum support you know that you will take by then. But if it's unbounded, then you have the trouble, you don't know to get the factor.
That's right.
And then the least sequence and all the
if it's varying all the time, then I don't even quite know how to pose the system. You know, I kind of had trouble writing the question down. So if it's varying once, I don't know what the delay at node 3 is, but it'll always be the same once I figure it out, I would. Then we can just test until we learn it and we're good. But if it's varying at every time step, then it's hard to even write down what the question is in a concrete way. So I don't know the answer in that case. Thank you. More questions? Okay, I promised it was simple. Was it simple? Yeah. I hope. Maybe. All right. So, is this a contradiction of any of the prior results? No. Those prior results, as far as I know, are all correct, but they make different assumptions. In particular, the causality constraint is enormous. It really changes the answers in all of these questions. The punchline about this topic is that we can show that the capacity of one network is a subset or equal to the capacity of another network, even if we can't find either capacity region. That's a very powerful tool. It turns out in other problems, we use the tool not to talk about capacity regions, but to talk about code design. In particular, we can show that the code design for a network A, if you could figure out how to do code design on a network type A, that in some cases would solve code design for networks in the family B. So that you can just study one, and that'll be enough to give the answers to the other as well. And that's another kind of reductive argument. You might think that knowing how to do this reductive argument would also tell you how to do that one, but so far at least, we don't always know how to turn arguments for one into arguments for the other, and I'll tell you more about that tomorrow probably. The key though is that reduction is a great tool for solving hard problems, or maybe more accurately, reduction is a great tool for avoiding hard problems, because I never found what the capacity is. I just found a way around finding what the capacity is, and yet can make really powerful statements about not just one network or two networks or a special family of networks, but in some cases about all networks in a very large class, using arguments that are much, much simpler than actually finding any capacity region. All right, I am at 10 minutes before my official end time, and I suggest that we go to questions now, because otherwise I'll be sort of mid-sentence when the time runs out, and we can pick up with it next time. So I'm happy to take any and all questions.
The reductions you're making is not
reversible operation?
They do not all go in both directions, but sometimes we can go in both directions, and the delay argument was one. I mean, one direction was trivial and the other was more interesting. But in some cases we just play the game in both directions and show that both problems solve each other. And in other cases, we can only show one way, which in some sense bounds one by the other.
I have a request.
Please.
But we adopt a secrecy strategy for this work because we should never allow a bureaucrat to listen that delay does not affect capacity.
Yes, it's not a lesson we want them to learn, but somehow I get the impression they already know. Other questions, please.
So, do you think your model can take into account the feedback?
Absolutely. So our model had every node having both outputs and inputs that depend on each other, so there's no problem with feedback. But if you had a non-causal model where your feedback got there instantly, you will certainly, in some cases, do better than if you have to wait, like you have to wait for every channel output. So that's where it comes into play. Question?
But these reduction techniques, we already use many of them, not in maybe large networks, but to find outer bounds and inner bounds. For
Absolutely. Reductive strategies are by no means new, but they are not as heavily used in information theory and not used to as great advantage as I think they could be. So I am not by any means suggesting I invented this strategy. In fact, one of the early slides said a very old and simple strategy. It is by no means new, but it's deceptively simple, so people think, what could you possibly get? And enormously powerful. You can really make statements about the whole family of networks or large classes of networks that would be very hard to prove case by case, which has been the major strategy that information theory has employed. So no, it's by no means new, either in information theory or outside of information theory. I'm just plugging it as a useful tool, but not a new useful tool. Other questions? Please. I can't hear. A little louder?
Can you handle non-integer delays?
Can I handle non-integer delays? Non-integer delays are not defined in this model. You know, I had time steps that were integers, so I don't know what a half of a delay means. If a half delay means that I'll certainly have it by time 1 and the rest of my model doesn't change, then yes. But if it means something more subtle, then I don't know.
Can you generalize to non-slotted communication?
Yeah, non-slotted communications, the short answer is I don't know. I suspect if it's still very systematic and the delays are regular, then it shouldn't be a problem. That whatever you were doing at time t, you know, that you can still play this game, but I'm not sure. I haven't worked on that problem. Question?
At the beginning, you said you want to characterize the region in between the small number of nodes and the asymptotic regime of number of nodes. But now in the delays, you're still assuming asymptotic.
Not in the number of nodes. So this result applies for a 1,000,000 node network today. It tells you something about the capacity of a 1,000,000 node network, as well as a 1,000,000,000 node network, as well as a 3-node network. It applies to all of them. The asymptotics in the definition of capacity, you're right, I haven't gotten rid of. That would be another interesting topic that people are working on, but isn't addressed here. But you are correct that the asymptotics in block length hasn't gone away, but I said number of nodes in the network, and this is not asymptotic at all. This applies for every m, which was the number of nodes. Yeah. And by the way, for all of you who are asking all these great questions that I don't know the answer to, that this can be your next paper. Other questions? Well, thank you all, and I will see you tomorrow.